A very good afternoon and warm welcome to this live session. I'm Dr. Vaibhav Pandit and today we are going to discuss the topic that is titled here Fundamental Morphology Operations. So far this is the 15th live session for the subject image processing, also known by digital image processing and also for advanced digital image processing. So this is one of the core topic morphology operations here. So for the morphology operations, the fundamental operations here today we are going to discuss here. So basically, as we have the title fundamental morphology operation, you should have a background of morphological understanding. Morphology means what? So that I will talk first of all, and I just now clear I'm going to focus more onto the two operations because these are the fundamental ones, and using these two fundamental operations rest of the morphology based algorithms for image processing applications are developed. So I just tell you the names. The fundamental morphology operations are the two. Those are erosion and then that the dilation here. So let us first of all just have brief idea of the term morphology, and then we move on for the details of the erosion and dilation, and for the two I will also have a practice with respect to few of the problems those generally you find into your examination here. So let us have introduction to the term morphology here. When we talk the term morphology, this is the word that is commonly denoting the branch of biology basically, and it deals with the form and structure of the animals and plant. So here you just have the understanding that morph means form or structure of the animal. Form means a kind of shape, how much big, how much small it is there. So that kind of studies for the animals and plants, of course, into the biology is said to be the morphology here. Now this morphology term is also adopted in mathematical terms for engineering applications here. So the same term morphology is here. So in the context of mathematical morphology, we have certain details, and of course especially in the context of our subject, that it is image processing here. So with the help of morphological operations here, there it is possible the extraction of the image information, that is of course we are intended to find because it is useful here. So extraction of the various kind of the image information or the image components you say is made possible with the help of the morphological operation here. So this is of course in the representation and description of the region shape. As we have our image, so image will be covering various objects and of course the boundaries associated to those objects that separate the object from the background here. So the boundaries, the skeletons and the convex hull, so these are all the parts associated to the form and the structure of the object inside the image. Hence we have this morphological image processing operations here. So because of this particular reason, the morphological operations can be used to remove the imperfections into the image and provide information on the form and structure of the image. So this is basically taking us to one of the popular application of morphological image processing operations into the domain of signal processing, and especially the two-dimensional signal processing, that it is image processing here. So here I just show you the visualization for the example here. So if we have the image that is obtained after performing the segmentation here. So image segmentation is also one of the fundamental operation that we can perform. So various fundamental operations we have studied, that it is first of all the enhancement we can do in the spatial domain, in the frequency domain, image restoration we have understood, color image processing, image compression. So like that there it is image segmentation also. So see, the example image is of a fingerprint here. So in the fingerprint identification applications here, for identification and further authentication purpose, matching should be there. So for matching of the sample image with the reference image, there should not be the presence of the noise. So in this particular image, whatever the curves you see with the white color, so it is the pattern of the fingerprint here, and in this complete image, whatever the small dots into the white color you see, this is the noise here. So basically for identification and authentication purposes, we perform image segmentation that separates out a simple object from the background into the image here. So just performing image segmentation is not enough. So it has not removed all the noise particles from the original image here, original information here. So for that purpose, along with image segmentation, if we perform the morphological processing operations here, so that time we get the output like this. So you see here, there are no small white dots in the image that you see on the right hand side. This is obtained by first of all performing the image segmentation as it was done in the previous case on the left hand side, but it has followed by the morphological processing here. Now you see the image is free from noise here, and further application will be at the efficient use here. So this is what the significance of having the morphological operations done for the image processing applications here. Now coming back to the context with respect to the mathematical logics, because of the mathematical logics we are able to apply it onto the two-dimensional signal here. So the language of the mathematical morphology, I hope all of you know from your school days or from junior college days, is the set theory here. So union of two sets or the intersection of two sets, various definitions and further operations we can do in the set theory. Okay, so all such logical things we need to do in the morphological image processing operation, and of course for the fundamental operations also that I am going to deal, that it is the erosion and the dilation here. Now this mathematical morphology to be the set theory sets, we have the mathematical morphology representing the objects into the image here. So let us take a discussion for one example here, where the set of all the black pixels into the binary image is a complete morphological description of the image. Various types of the images we have studied: binary image, then there it was the grayscale image, and then there it was the color image here. So if we take the binary image, we have the two options only, either the white color or that of the black color here. So in such, for example, the binary image, if we collect all the black pixels, it will form a set. So let us say this is just the object inside the image here. And in the binary image, the sets are members of the two-dimensional integer space. In the set theory, here it is the practice to represent the space as z square here. I hope you know the space very well. The space we can define in 2 dimensions, in 3 dimension, in multi-dimension also. So for the binary images, as we have the 2 dimensions to hold and represent that information, so the 2D integer space is represented by z square, and with respect to this space, we are going to have the definition of the fundamental morphological operations. Those are erosion and dilation using the set theory background here. So here each element of the set is tuple whose coordinates are like the x and y for the black pixel into the image here. Now if we extend the binary image processing with the help of the morphological operations to the next level of the grayscale images here and further the digital images, so these can be represented as sets whose components are into the space defined here by z cube here. So here we are going towards more complexity with the increase of one more dimension. So from 2-dimensional case we are moving to the 3-dimensional case here. More information with respect to this regard we can give as The two components of each element of the set refer to the coordinates of a pixel, and the third component which is being added corresponds to the discrete gray level value. Gray level value means the intensity level here. So sets into the higher dimensional spaces can contain the other image attributes such as the color and time varying components here. So this is what the information we have shared with respect to the morphology term here. So if we have the proper background of the morphology here, we can now start with the exact fundamental morphology operations for image processing here. The first operation is called as erosion. So this is Erosion here. Along with erosion, there it is another operation also which is fundamental here. So these are the two operations. One is the erosion that now I am going to discuss about, and the another one is dilation here. So these are the two operations very important and what we call fundamental operation. After erosion and dilation, there are also two more operations sometimes referred to as the hybrid operations. So these are opening and closing, and using the four: erosion, then dilation, then opening and the closing, certain more algorithms into the morphological image processing we can achieve here. So this is what the point in written form. Many of the morphological algorithms are based on these two primitive operations here. Now let us have the definition by using the set theory background for the operation erosion here. Now, as in the set theory, the common things are collected together and they are said to be set A, set B here. So, likewise, we are going to have the set here. So, for example, we have the two sets denoted by capital A and capital B into the space defined for two-dimensional case here. So, for two-dimensional case, here we have the space defined to be z square here, and let us say the sets are capital A and capital B here. So here we are required to perform erosion of the original image. So let us say capital A is the original image and B is the operator image that operates onto the original image to find the erased version here. So in general way we can say that erosion of A by the structuring element or kernel or the mask or the convolutional template, that is being the names for capital B here, and this is what the symbolic representation of the erosion operation. So we have the image capital A to be operated for erosion with the use of structuring element capital B, and in between the two we have a circle which has inside the minus sign here. The definition as per the set theory here we provide. So A erased by B, as it is the set theory, the definitions in mathematical representation are there inside the curly brackets here, and Z is the parameter of defining the two-dimensional space, and here B suffix Z is the reflection of the operation that we are going to perform, and this is said to be the subset of capital A. The more details let us see here. Yes, one student is there, Dhaneshwar Jadhav. Yes, Dhaneshwar, this is the topic fundamental morphology operations, and I have started to discuss the details of the first fundamental morphology operation, that it is erosion here, and after that I will be taking a problem for practice purpose also, and also I shall deal with the second fundamental operation called as dilation, and if the time permits I will also talk about opening and closing along with the examples here. So now let us continue here. The definition of erosion. So mathematically using the set theory I can outline like this. In words here we can talk about, this is the equation that indicate the erosion of A by B is basically the set of all points such that B translated by the parameter z is contained in A. Here you see from the set theory we have this particular symbolic notation. This symbolic notation is just to mention that whatever we have on the left side, this is a part of the right hand side. So right hand side is a bigger set, and all the constituents onto the set that we have on the left hand side are actually the part of the larger set that is represented on the right hand side. So this is subset of. So this is what the word definition here. So the set of all the points such that B translated by Z is contained into the original image capital A here. So this is the equation, that is the basic definition of the erosion here. The more information step by step we will share with you. This equation is usually favored in the practical implementations of the morphology, and for better understanding here we are going to take the help of one figure here that will describe you the erosion process here. I was just now talking about capital A and capital B here. Now let us have the example here. So this is what the example. This example is having 5 parts here. So here you see part A is the set A. So this is what the set A that is shown to you people. So this is some kind of the image information in this much of the area that is represented by capital A here. So this is one input that is required to perform erosion. So erosion is to be performed on capital A here. Now what is going to help the erosion? That it is the structuring element. The structuring element here, it is having the square shape here. The structuring element may have a square shape, it may have a rectangular shape, it may have a circular shape here. So depending on the type of the structuring element, the corresponding results of the erosions are also going to change, and the selection of the structuring element should be suitable to the application at hand here. So the square shaped structuring element here it is shown here. Now I just compare the dimensional details for the two inputs here. So for erosion operation we require capital A and we require capital B as well here. So if the dimension of A is small d, the dimension of B is d by 4 here. So it is 1/4 the dimension of the original image that is to be erased here. That is why here it is mentioned d by 4 here. And what the dot you see at the center, so this is the origin of the structuring element. While operating this structuring element onto the image plane like this, we have to match the origins of the image and that of the structuring element, and then we have to shift it from left to right, and this we have to carry out for every row here. So that will be of course detailed here. Now you see, I hope part A and part B are clear to you people. These are the two input things here which are required for carrying out the erosion process here. Now after the erosion is carried out, the output is represented into the part C. So this is the part C. So you see, this is what the shaded portion. So the outline is already shown to you people. This is what the shaded portion, and you see the dimensions. The dimensions are 3/4 of the D here. So what the dimension it was originally for A by small d, it is not here for the resultant, that is the erased version. And you see the erased version is denoted symbolically as A erased by B here. So in between the symbolic notations of A and B, we have a circle, and inside the circle there it is a negative sign here. So this is what the dashed line is basically representing the expected dimensions of the original image to be erased here, and the current dimension that we obtained after the erosion is less than that. So there it is a loss of d by 8 on one side d by 8 on another side here. Now, if we change the type of the structuring element, so instead of making the use of B like this, which is of the square shape, if we have a rectangular shape here, here it is as shown elongated here. So the elongated structuring element is shown here in the part D here. Now, operating the input image A with the help of the structuring element B here, we obtain the result of the erosion, and that is shown here. So erosion of A using the elongated version, you are just finding a line. So this is the line, that is A erased by B here. Now the dimensions are represented here, it is 3D by 4, just the length of the line here. And now you see the elongated dimension, the bigger dimension of the structuring element here, here it is small d here, so it is equal to the side of the input image. So that time we are obtaining this kind of result here. See, for part A, B, C, D and E, we have a written discussion here. I will just give you the brief idea. So set A is shown as the dashed line for the reference in figure C. The locus of the points, locus, we are finding a group of points here within the boundary that constitute the erosion of A by B here. And the figure D is showing the elongated structure, another type of the structuring element here. And next to that figure it shows the erased version of the same, and the original set was eroded down to a line. So what it was a two-dimensional object, it has become one-dimensional after the erosion operation here. Now along with the erosion, there it is another fundamental morphological operation which is known by the name dilation here. So the details of dilation we shall definitely see here. And for more information of yours, erosion and dilation are said to be duals of each other, and this is of course with respect to the set complementation and reflection, where the same structuring element is utilized for performing the dilation operation and erosion operation. Most of the time in your examination the question comes that prove that dilation and erosion are the two fundamental morphological operations which are duals of each other. So that time we are taking the help from the definition of the erosion and then further the definition of the dilation here, and we will prove that. So here we have the definition, representation of first of all the erosion and then the dilation, the relation between the two here I show you. So inside the bracket you see capital A erased by capital B, and to this bracket here it is power mentioned to be small c. So small c is representing complement. So complement means taking those elements from the parent set which are not the constituents of the one that you are showing inside the bracket here. So this is what the complement here. So the complement of A erased by B is equal to A complement dilated by B cap here. So this is what the reflection here, and you see I have made it familiar with the symbol of erosion. Symbol of erosion is, there it is minus sign inside a circle, whereas for dilation there it is plus sign inside the circle here. Now for proving this particular result here, we have to start with the definition of the erosion that we have already given, and now I just substitute that particular definition inside the bracket here. So inside the bracket, as we have A erased by B, this is what the definition, and to this definition we provide complement here. So to the power we shall be writing C here. Now if the set, here we have on the right hand side B suffix Z is contained into the original set A, so then we have BZ intersection A complement is equal to phi. So as per the set theory, phi means null set. Null set means it is the empty set, it does not have any element inside. So in this case, the preceding equation will be represented as, we have A eros by B, then complement, that is equal to, we have Z, then BZ intersection A complement, that is equal to phi here. But the complement of the set of z's that satisfy the condition, here we have bz intersection a complement is equal to phi, as discussed above, is the set of z's such that bz intersection a complement not equal to phi here. So therefore we have to represent the A eros by B complement is equal to Z BZ intersection A complement, that is not equal to phi, so that it is A complement, that is dilated by B cap here. So this proof you can give as the answer to such type of the question here. So I have just taken selected steps here. You can also elaborate the steps as per the weightage provided to this particular question in your examination here. So this is the general question usually asked for the erosion here. Next to that, I will discuss about one example related to the erosion here, and that will show you the practical effects of the erosion operation onto the binary images here. So here it is, one of the simplest uses of the erosion for just eliminating the irrelevant detail from a binary image here. In the beginning, while introducing morphology and its application to the binary images, the noise removal, the case I have taken thereupon, so it is of the similar kind here. So we have A, B and C, the three parts in this illustration here. Now you see in the part A, the part A is here. So in this part A, we have the image displayed, binary image having various squares. The size of the square in terms of the pixels are 1 pixel only, 3 by 3 pixels, 5 by 5 pixels, 7 by 7 pixels, 9 by 9 pixels and 15 by 15 pixels. So here you see few of the squares are small in size, few of the squares are big in size. So as for this label, we find that biggest size is 15 here. Now you can identify there are three squares. This is the 1, this is the 2 and this is the 3, which are biggest inside the input image here. Now, if the erosion operation for such input image is performed, so for performing the erosion operation, we need the help from the structuring element. So, if the structuring element is having the dimensions of 1s and 13 pixels on the side here, so the resultant image we obtain like this here. But now we are focused on to just visualizing the squares with the pixel size 15 by 15. So that time, if for such an erased image, if we perform the dilation operation, so the same structuring element is used, so that time we obtain the output image like this, that is shown in the part C here. So in the part C, you see there it is the complete black and only the three white colored squares are represented. So these were the intended squares that we wanted to visualize. So with the help of the erosion and further the dilation, we have obtained the things here. So now here we are going to just solve one problem based on to the erosion here. So here it is, the problem statement, very simple. The input image and the structuring element are given below. Find the eroded version of the input image. So these are provided to us. So see, as per the problem statement, here we have the input image. The input image is shown like this. So these are the two dimensions to this input image. and also we are provided the structuring element here. So this is what the structuring element here. Now you can count here. Here we have 1 2 3 4 5 6 7 8, and 1 2 3 4 5 6 7, and I think one more here. Yes. So the 8 by 8 is the original image here, and now here we have the structuring element 2 by 2 here. So here we have two rows and two columns, and you see the white dot. White dot is just representing center or the origin of this structuring element while we match it onto the image plane here. So what we need to do, we need to find the eroded version of the input image here. So let us have the solution to this particular question stepwise here. So we have step number 1. In step number 1, what we are going to do, the structuring element here we are going to compare with the input image. So both the things are provided to us from the problem statement here, and while comparison, if we find all the pixels into the structuring element overlap with the input image, then the origin corresponds to the input image pixel will be turned on. So it is basically producing that much portion of the output which is matched with the structuring element here. If it is not matched, that means otherwise condition, the pixel is not appearing into the output, so the pixel is turned off here. So in the given example, the structuring element is shifted from left hand side to the right hand side here, and initially here we have no pixels overlapping between the structuring element and the input image, so the output image is shown below the first iteration here. So here we show with the help of the illustration. So this is what the structuring element that it was provided to us, and this structuring element we are just have started from the first pixel and we have to go left to right here. So while we match this particular origin of the structuring element that it is shown by the white dot, there it is no dark pixel at this particular place here. So there it is no matching. That is why in the output image no dark pixel is shown to you. One thing should be there in your mind. This is the binary input image to be eroded here, and whatever you see the letter H with the help of the dark pixels here, this is what the object here. So with the help of this problem you have to study what changes are made onto the form of, onto the size, onto the shape of the object inside the image here with the help of the erosion operation here. So here this is what the first step we have started to match the structuring element to the image plane at its origin here. So for any original image, the origin is at the left hand side uppermost corner, the first pixel. So this is the origin of the image plane. This is the origin of the structuring element as provided here. That we can vary with respect to the application. We can define the corresponding structuring element that will better operate onto the image to obtain the desired form of the resultant image visualization here. So this we have done, and in this particular matching we have not found any overlapping of the dark pixels, and that is why in the output we have nothing here. Now we move further. So as the first row we have, and we have matched to the first cell only, we have to get the input image that is not perfectly overlapped with the structuring element, and therefore all the pixels of the output image in the first row are currently shown to be the off with no dark pixel. So we have to go for step 2 here. So in step 2, the structuring element is mapped with the second row of the input image. So initially we find no perfect matching. So therefore we shift one pixel towards the right hand side here, and after one shift towards the right we find a perfect match, and hence the output of the image pixel is turned black, which is illustrated into the next visualization. So here we see. So the theme is, in the first row there it was no dark pixel from left to right. That is why into the output there was no dark pixel, because we don't find any kind of overlapping for the structuring element and the first row of the image plane. Now we have shifted to the second row here. In the second row, the first pixel you see, so here it is white, here it is dark. So again there it is no matching here. So that time we have to shift from left to right. So here we find dark pixel, here it is also the dark pixel. So as the matching is there for the central position of the structuring element, here we show it with the help of dark color here. So this is the step 2, and then we can move on to the right hand side and then to the next row in the same fashion here. So let us have the next step, that it is step 3 here. So in the step 3, the above process we are supposed to repeat till the last pixel entry into the input image plane. So the eroded image, after we perform this repeated process here, reaching the last pixel into the image plane here we are getting the visualization of the resultant. So this was the input image plane, and which has been operated by the structuring element, and this fashion we have gone. So from left to right in every row here we have found the overlappings, and when the overlappings were matched here, so for the dark pixels here, so that time we have generated the result here, and this is what the result you see. So this is the result you see, whatever the object that it was the letter H. So with the erosion operation here, again there it is the letter H, but it has shrinked here. So this is what the result definitely we shall be discussing here. In general I will tell you, with the help of the erosion operation the object shrinking is there, whereas if you perform the dilation operation, so that time the object will be somewhat expanded here. So now after the thorough understanding of the erosion operation here, that is one of the fundamental morphological operation, we switch to the next one. So the next operation is called as dilation. Basically the dilation operation is very reverse to what we have done in the case of erosion here. So both are reverse to each other. Dilation is opposite to the erosion, erosion is opposite to the dilation here. So let us first of all have the definition of dilation operation according to the set theory. So in the set theory we have to make the definition considering the two-dimensional space here. So the two-dimensional space we have to represent as z square. The two inputs here we are going to take, those are capital A and capital B. So if we have capital A and capital B to be the two input sets into the z square dimensional space, so that time the dilation operation of the input capital A in general by structuring element capital B will be denoted by this symbol. So A and B, and in between the two there it is plus sign inside a circle. The definition as per the set theory, here it is shown, the notation is on the left hand side, and inside the curly brackets here we have the Z translated parameter, B cap its reflected version, having intersection with the original image capital A not equal to phi. Not equal to phi means this intersection is not empty here. So this is the equation that is based on obtaining the reflection of B about its origin and shifting this reflection by the parameter Z here. The dilation of A by B is then the set of all the displacements Z such that the B cap and capital A overlap by at least one element. So into the examinations, if you are asked to write down the details with respect to the fundamental morphological operation, you just write down the definitions of the erosion and dilation as I have shown in the set theory form here, and into the words also you have to explain here. So based on to what the interpretation we take from the dilation here that we have represented into the above equation, we can rewrite this particular definition, and this definition is like A dilated by B in the set. For the Z we have BZ cap interpolated with A subset of A here. So the set B is commonly referred to as the structuring element, as I have already discussed before, and this is true for the dilation, erosion, opening, closing, whatever the morphological image processing operations you take here. Now it is more intuitive when the structuring element B is viewed as a convolution mask. So let us have the comparison of the structuring element to the procedure we are following in convolution operation here. The procedure of morphological operation with the help of the structuring element that just now you have seen here, it is like what we have done into the spatial filtering also. The spatial filtering we have discussed for image enhancement, and then for the image restoration also. Thereupon also it was certain kind of mask or template or kernel, so that we have matched onto the image plane from its origin at the upper left corner to left to right, all the rows thereupon we had scanned here. So a comparison of the convolution to the dilation operation can be like here. So although the dilation is based on the set operation as we have discussed, whereas convolution it is basically from the arithmetic operation, the basic process of flipping or sliding the structuring element B about its origin and then successively displacing it so that it slides over the set image A is analogous to the convolution process. Hence, sometimes it is the name given to. Now, here we are going to make the use of one again example illustration that will show you the effect of dilation onto the original image plane here. So we have again 5 parts as we discussed in the case of erosion operation here. So now this is for the dilation operation here. So we have parts A, B, C, D and E here. So part A will show a simple set and part B will show the structuring element and corresponding reflection here. So this is what the example illustration here. Now you see this is the set A with square shape. The dimensions are shown small d by small d. So this is the set A here, and now it has to be dilated with the help of the structuring element here, which is also of the square shape. The dimensions are d by 4, d by 4, and the reflection B cap, it is represented by B here. At the center you see the dark dot, that it is the origin of the structuring element here. Now when we perform the dilation of the original set capital A with the help of this structuring element, so the corresponding dilated result is shown in the part C here. So this is the part C. Now you see the original dimension, it was D like this. It has enhanced by D by 8 on the right hand side, D by 8 on the left hand side, D by 8 on the top and D by 8 on the bottom here. So dilation basically expands the size of the object under dilation operation here. Now as it was done with respect to the erosion, if we change the structuring element, instead of this structuring element which is of the square size, if we select the elongated type of the structuring element as shown here with the dimension small d on the larger side here, so the dilated result for the given set A is shown here. So here of course instead of having the dimension small d, we have d by 8, d by 8 increased on both the sides, left and right, whereas for the top we have d by 2 increase, and the bottom also d by 2 is increased. The inside, that it is shown by the dashed line that I am going to outline here. Here it is what the original shape of the set A it was. Now let us talk about one example here, and the example, before going to that example, let us have the written information with respect to the illustration that I have just now shown to you. So in the case that we discussed, the structuring element and the corresponding reflection are equal because B is symmetric with respect to the origin. More details you can see in my original videos that we have on the online platform. The dash line into the part C is the original set. I have also outlined the same that you have seen here, and all the points inside the boundary constitute the dilation of A by B. And figure D, the fourth one, shows the structuring element of elongated type here, and the corresponding result you see in the part E here. So this was the example we discussed. Now coming to the example of the dilation here. So the best example for the dilation can be bridging of the gaps in the text here. So this is what the example. So here we discuss part A, B and C here. So on the left hand side, you see there it is certain sample text which is displayed with certain poor level of the resolution with the broken characters here. So this is what the part A of the image. So here you can read few of the things, but you see these particular words and letters, especially if you have the magnified view like this, we have this E to be broken. It should be a complete E like this. The A should also be complete A like this here. So now here we are going to make the use of the structuring element B as represented like this. Here you see the size of the structuring element is 3 by 3. At the middle the value is 1 here. Its adjacents to the top, bottom, left and right are also with the value 1, whereas the diagonal cells are represented with the value 0. So this is the structuring element, and this structuring element is operated over this image plane that is having text to be displayed here. So after the dilation operation, we get the outcome of dilation is displayed in this particular image plane here. You see, as compared to the earlier case, we have the bold letter with the same kind of the text here, and when we see the magnified view for this, you see such a kind of joining we have for the letter E, for the letter A at these places where it was broken. So this is what the advantage of using the dilation operation. So this is what one of the application of having the dilation operation for bridging the gaps in the broken letters here. Now let us take one practice problem here. So the problem statement here we are providing. The problem statement is using the input image and structuring element as given below, find the dilated version of the input image. So here we are provided the input image and the corresponding structuring element. So this is the input image. Input image here we have. So for the input image, you see there are 7 columns, and we have here total 1 2 3 4 5 6 7 7 rows, 7 column, and this is what the structuring element. The structuring element is of the dimension 2 by 2, and the white dot you see in the first cell that is dark here, this is the center of the structuring element here. If the size of the structuring element is odd, as like 3 by 3, 5 by 5, 7 by 7, 9 by 9, 11 by 11. So that time basically the middle pixel into the middle row, middle column is selected to be the center of the pixel here. But in this type of the style here it is what the center of the structuring element with the even dimension here. So we are asked to find the dilated version of the input image here. So let us find the solution stepwise as we had done for the case of erosion here. So here we are going to follow the step number 1. So the step number 1 will be first of all to make comparison of the structuring element with the complete input image plane at the match of the center point here. So if we find any kind of overlapping component between the structuring element and the input image, we can mark it with the help of asterisk here, and then origin of the structuring element corresponding to the input pixel we have to make on into the output visualization here. So let us have the illustration of the step 1 here. So as this is the input image plane here, and to this input image plane as we are matching the structuring element like this here. So you see, if this pixel is matched to the first pixel, there it is no overlapping because this is dark here, this is white here, and here it is a match here. So as this is match at the central position, as this is the center of the structuring element origin and the origin of the image plane, we have to make this on here. So this is just the step 1 here. Then we go for step 2. In step 2 we have to shift the structuring element over the input image from left hand side to the right hand side, and the position of the structuring element as shifted we have to go by. So there is no overlapping between the two for the second step here. So the structuring element origin corresponding to the input pixel will not be is turned to on. So therefore there is no change for the previous output image here. So here we see the visualization. So now you see this is what the portion focused while we overlap the image plane by the structuring element. So for both the dark pixels, especially for the central one, you find whiteness here. That is why there it is no dark pixel on into the output image here. So this is what the step 2 here. Next we go for step 3 here. In the step 3, as we have done previously, the similar things we have to carry out. The structuring element we have to shift towards the right hand side of the input image to find any overlapping. If it is present or not, we have to check, and in this case the overlapping, if it is present, so the corresponding input pixel will be turned to on and the resultant image can be shown here. So here we show the resultant image for step number 3 here. So in the step number 3, you see this is the structuring element that is covering this much of the portion here. So you find there it is a match. There it is a match between the dark pixels of the structuring element and the original image plane here. That is why at the third place here we make dark pixel here. So this was the thing here, and now we move on to the next step, that is step number 4. So here another structuring element is again shifted to the right hand side of the input image to find any kind of the overlapping here, and there is an overlapping and the resultant image we show. So here we find the illustration. Here we have the same illustration. Here we have the next illustration we have to go for. We also discussed step number 5. After one shift towards the right, there is no overlapping and hence the output image will not be changed here. The next shift over the image input is on the boundary, and so this will not be matched with the structuring element and finally the next shift is from top to bottom, which is shown here. So here we go. So in the previous illustration it should be a match, and that should produce the black color here, and as we have shifted to the next row, this much of the image portion here we have obtained, and thereupon we find a mapping, so that we have shown with the help of the asterisk here, and because of the matching here we have this pixel also dark here. So this is what the illustration for step number 5 here, resulting output here, and the output at this particular pixel to be dark here, it is because of the step number 4 here. So we go for the next step, that it is step 6 here. So the above process we have to repeat to get the final output of the image, and that we can output here we obtain as like this. So this is what the structuring element, and from left hand side to the right hand side in every row like this, if we go, we come to the last pixel of the image plane here. So we have reached to the last pixel here. This plane, this much of the portion is mapped here, and you see because of this much of the overlappings here, the corresponding results we have shown in this output image here. So this was the step 6 here. So this was the example of the dilation problem also we have studied about. So erosion and the dilation are the two fundamental morphological operations. I think one point is very clear to you people, that the dilation expands an object inside the image, whereas erosion shrinks the object inside the image here. These are the basically the operations developed for the binary images here, but as we have the images evolved from binary image to the grayscale image to the color image, from color image to the multispectral image, the applicability of the morphological image processing operations is also tested many a times here, and with brief modifications it is also extended up to the multispectral and further hyperspectral images, if also it is there being checked here. So now I am just giving you a brief introduction to the other two hybrid operations which are based on the dilation and the erosion operation here. So these are called as the opening and closing operation here. So I have just talked about dilation expands the image, whereas erosion shrinks the image. Now we have the opening and closing. So the features with respect to opening and closing, I tell you, opening basically smooths the counter of the object. Counter means the edge, and it breaks narrow isthmuses and eliminates thin protrusions here. Whereas closing, if you talk about closing, tends to smooth the sections of the contours, but as opposed to the opening operation, it generally fuses narrow breaks and long thin gulfs, eliminating small holes and filling up the gaps in the contour here. The definitions from the set theory background for opening and the closing operation I can give you. So the opening of set A by the structuring element capital B in general can be denoted by the symbol A circle B here. A circle B, there it is, a symbol of circle in between the two letters capital A and capital B here, and here it is the definition of opening here. So this is A opened by the structuring element B here. So first of all we are going to perform erosion over A by the structuring element B here, and whatever the result we obtain, that we have shown inside the parenthesis here, that result we dilate with the help of the structuring element B here, the same structuring element. So first of all, erosion of input image and dilation of the eroded version is nothing but opening operation here. So this is what. erosion of A by B followed by dilation of the result by B is the opening operation. Now we have the definition for closing. It is also similar one. First of all, how it is denoted. See, the capital A closed by the structuring element B here. So we have to show a dark dot in between capital A and capital B here. So the definition here we provide. So this is A eroded by capital B. So first of all, we have to perform dilation of A by the use of structuring element B, and the dilated version is then further eroded by capital B here. So here it is the dilation sign and here it is the erosion sign. So this is completely reversal to what we have seen in the previous case here. So for opening, we have first of all erosion followed by dilation. Whereas for closing, first of all we have dilation followed by erosion here. So these are the two definitions of opening and closing, and how the opening and closing are having the effects onto the image plane for smoothing, sharpening, that I just tell you briefly. See, first of all for the opening here. So opening operation is having the simple geometric interpretation with the help of this example where we have the three parts. The first part, you see the shaded portion to be the structuring element capital B here, and capital A is the triangular image plane object here. So structuring element B we have to roll along the inner boundary of A here. So what will happen in the part B, you see the heavy line is the outer boundary of the opening here. So these curvatures you find instead of the sharp corners of the triangle here, and the complete opening will be shown by the shaded portion. So instead of having a triangle with the sharp corners, the corners are smooth as a result of the opening here. So this is what discussed in words here, and after this we have the closing operation also discussed here. So for the closing operation, the similar kind of geometric interpretation we need to make, and here you see this is the image plane capital A here, and this is the structuring element B here. So in these two examples, the structuring element shape is selected to be of circular here. So here the structuring element B is rolled onto the outer boundary of A, whereas it was onto the inner boundary of A in the case of opening here. So as we roll up here and we fill this much of the gap here, so that time the heavy line that is showing you this kind of structure is just rolling the structuring element onto the outer boundary, and this is what the complete shaded portion that you see. So what it was a sharp valley inside the input image plane here, now it has been smooth here at this. So there it has been filling up the information in this particular gap here. So this is what the closing operation here. And as like we have the dilation and erosion operations to be duals of each other, sometimes into the examinations you are asked to prove that the erosion and dilation are duals of each other. A brief proof I have provided in this session. Similarly, the opening and closing are also the duals of each other here, and that also we can prove with the help of the simple proof here. So for more details you can attend my lectures, those are already there on the online platform of Ekeeda. By the next week we shall definitely meet with one more topic from morphological image processing. So I hope all your ideas are clear with respect to these topics. Thank you.